everyone, welcome to iTTV. For today's lesson, we'll be studying on oxidation and reduction. So, for today's lesson, by the end of the topic, students should have a better understanding of, the ability of displacement reactions to happen, as well as the electrochemical series. So with that, let us start off by looking at how iron 2 ions can change to iron 3 ions, as in a change in oxidation number can take place easily with regards to the iron ion, as well as how iron 3 ions can change back to iron 2 ions. So, if you look at the slide, there is a simple experiment whereby iron 2 sulfate is reacted with bromine solution or bromine water. So in the test tube, it contains light green iron 2 solution, whereby bromine solution, which is brown in color, is added drop by drop into the solution. So the first observation would be the light green color actually changes to brown. So in the third test tube, as you can see, it's actually the same test tube. Sodium hydroxide solution is added into the same test tube. And the second observation is that brown precipitate is produced. So, the simple demo as illustrated in the slide shows that iron 2 can be easily oxidized to iron 3 through the simple addition of an oxidizing agent such as bromine water or bromine solution that is brown color. So when we add an oxidizing agent together with iron 2, it will actually oxidize iron 2 to become iron 3. And iron 3 sulfate solution is actually brown in color. So that's why the first observation would be from green to brown. To further confirm the presence of iron 3 ions, sodium hydroxide was added, and therefore a brown precipitate was produced, and the brown precipitate is none other than iron 3 hydroxide. So let's look at the chemical reaction that has happened. Basically, the oxidation half equation would be iron 2 has been oxidized to iron 3. Whereas for the half equation for reduction reaction, bromine has gained 2 electrons to produce bromine ions. And the overall equation, upon addition of the oxidation and reduction half equations, would be 2 iron 2 plus reacts with 1 bromine molecule to produce 2 mole of iron 3 plus as well as 2 bromide ions. So, the substance oxidized for this experiment would be Fe2 plus, reason being because oxidation number of iron has increased from plus 2 to plus 3, while the substance reduced is actually bromine, and the reason being because the oxidation number of bromine has decreased from 0 to -1. The oxidizing agent in this case would be bromine, while the reducing agent would be Fe2 plus. So, in order to get the overall equation for this experiment, we need to make sure the number of electrons for both half equations are the same. So, let's look to the board to see how to derive the overall equation. So, the oxidation half equation was that Fe2 plus actually has become Fe3 plus. So Fe2 plus has released 1 electron to become Fe3 plus. So we would say that oxidation has taken place. Whereas for bromine, it would actually accept 2 electrons to become bromide ions, and we balance the equation with 2. So this one would be a reduction half equation, whereby bromine molecule has been reduced to become bromine ion. Now, in order to get the overall full equation, what we have to do is that we need to make sure the number of electrons for these two half equations are the same. This is 2 and this is 1. So therefore, this whole equation we need to multiply with 2. So therefore, we just multiply 2 inside. So this will be 2Fe2 plus. And we bring this down, bromine. And 2 electrons would cancel out each other because they are on opposite sides. And this one will also be 2 Fe3 plus. And this will be 2 bromide ions. So this is 2. This is also 2 because we had multiplied 2 inside. And we just write this down. 1 mole of bromine and 2 moles of bromide ions. So this is the overall equation for this experiment, and we would know that the oxidizing agent in this case is bromine because bromine has been reduced. And iron 2 plus in this case is the reducing agent because iron 2 plus has been oxidized. Always remember that the oxidizing agent, as we have covered in the previous lessons, that the oxidizing agent will always be reduced, whereas the reducing agent will always undergo oxidation in the reaction. So this is a very important point that students need to remember. Now, let's move on to how Fe3 plus can reconvert to Fe2 plus. So in the slide, you notice that there's a reaction of iron 3 chloride with zinc powder. So in one test tube, zinc is added into a solution of iron 3 chloride, which is brown color. And this test tube has to be heated, whereby the first observation noticed would be the brown iron 3 chloride has become light green in color, indicative of iron 2 plus that has formed. And sodium hydroxide solution is further added, and this gives you the second observation, which would be a green precipitate. And this means that Fe2 plus has reacted with the hydroxide ions to produce iron 2 hydroxide. Now, this second simple demo illustrates that it is so easy for the oxidation number of iron to change from +2 to +3, from +3 back to +2. So this demo is to show how iron 3 plus can be reduced back to iron 2 plus, whereby we just add zinc, which is a reducing agent. So it reduces iron 3 plus to iron 2 plus, and iron 2 plus is light green in color. To further verify the presence of iron 2 plus ions, we add aqueous sodium hydroxide, whereby we will get a green precipitate, which is indicative of iron 2 hydroxide. So this confirms the presence of iron 2 plus ions. So what are the equations that are formed? The oxidation half equation would be zinc has been oxidized to zinc 2 plus by zinc giving away 2 electrons, while the reduction half equation would be iron 3 plus has gained, received 1 electron to become iron 2 plus. And the overall equation is derived by adding up the two half equations. So zinc reacts with 2 moles of iron 3 plus to produce 2 moles of iron 2 plus as well as zinc 2 plus. Now, the substance oxidized in this case is zinc. Reason being because zinc has lost 2 electrons, while the substance reduced will be iron 3 plus because iron 3 plus has gained 1 electron. And the oxidizing agent, remember, is the agent that is reduced. So the substance reduced will be iron 3 plus, and the reducing agent will be zinc. Note, other reducing agents can be used to replace zinc, such as magnesium and aluminium. So, we can derive the overall equation using the same method as I've just now showed on board, that we need to make sure the number of electrons for both half equations are the same, and you just add up the two half equations. So remember that the oxidizing agent is always a substance reduced, while the reducing agent is always a substance that is oxidized. And the substance oxidized in this case is none other than zinc, because zinc has undergone oxidation to become zinc 2+. Zinc has released 2 electrons. So let's move on to the second learning outcome for today's lesson, which would be the electrochemical series. What is it? It's a list of metals according to their electropositivity. And electropositivity is the ability to lose electrons and become positive ions. So that is the definition of the electrochemical series. It actually shows a series of metals based on their electropositivity, which is the ability to actually lose electrons. So, if we look at the slide, there is another definition for electrochemical series, which is the arrangement of elements according to its ability to release electrons to form a positive ion, known as a cation. And the series is shown on the left-hand part of the slide. So, metals which are more electropositive and form positive ions easily by donating electrons. For example, it's easier for zinc to release 2 electrons to become zinc 2+. In a chemical cell, metals which are more electropositive will become the negative terminal, while metals which are less electropositive become the positive terminal. An example of a chemical cell is shown in the slide. And the further apart the two metals are situated in the electrochemical series, the higher the voltage of the chemical cell. For example, the zinc and copper chemical cell as shown in the slide. So, the electrochemical series can be seen in the slide, whereby metals which are more electropositive are situated higher as compared to metals which are less electropositive, meaning the higher position metals are able to become positive ions easier. They are able to lose their electrons easier than the elements that are below them. So, in an electrolytic cell, metal ions which are less electropositive will be selectively discharged, and you can see the setup of an electrolytic cell in the slide. So it's very important for students to differentiate between the chemical cell and the electrolytic cell. The most important point to note is that in a chemical cell, or known as a voltaic cell, usually the more electropositive metal will become negative terminal. While for an electrolytic cell, metal ions which are less electropositive, they are the ones which are selected and chosen to be discharged. So, if we look at displacement of metal, a more electropositive metal will displace a less electropositive metal from its salt solution. So this is the third area, because we looked at chemical cells, we looked at electrolytic cells. Now we look at displacement reaction, which is the third learning outcome for today's lesson. That always students need to take note that the more electropositive metal will displace, the term here is displace, not discharge, so will displace a less electropositive metal from its salt solution. So the more electropositive metal will act as the reducing agent. Reducing agent means that it will be oxidized. Oxidized meaning it will lose electrons to form positive ions. While ions of less electropositive metals will act as an oxidizing agent. And if it's an oxidizing agent, it will be reduced. It will be reduced means it will accept electrons. While doing so, the metal ions will be reduced to metal atoms. So that's just a bit of facts about what happens in a displacement reaction. And with that, I think it's good to show a simple demo to illustrate further on this displacement reaction. But before that, let's look at the slide that in displacement reactions, metals which are more electropositive will displace metals which are less electropositive from its salt solution. So the terminologies in this whole sentence is very important for exam purposes. So in the example that I will show very soon, I will have a test tube containing aqueous copper sulfate solution, and I will add zinc strip, a small strip of zinc metal into the test tube. And we should be able to see two observations. Because zinc, which is more electropositive, has displaced copper, the first observation would be a brown solid would be formed. Second observation would be intensity of blue solution decreases. So let's start the demo now for displacement reaction. So this is my test tube that I have prepared some aqueous copper 2 sulfate solution from copper 2 sulfate powder. And these are some pieces of zinc metal strips. So I will place one piece of zinc strip into this test tube that contains the copper sulfate solution. Because zinc is more electropositive than copper, it should be able to displace copper 2+ from its salt solution. So I will start now. I'll place this into the test tube and do a bit of shaking. Very fast, you will notice that you will see a bit of brownness being deposited on the zinc strip. Displacement reaction is slowly happening, okay, whereby zinc is displacing copper 2+ from the salt solution. So the brown deposit on the zinc strip should be copper metal, which is brown. And after 1 hour, 2 hours, the intensity of the blue color would be very drastically decreased. Okay, so this reaction takes time. We'll leave it for about 1 hour or a few hours. So this test tube shows the results immediately after the experiment, and we'll show you the results after 1 hour. So this is the result after 1 hour. As you can see, the intensity of the copper blue sulfate solution, blue color, has decreased, and there's so much brown deposits on the zinc metal. So these are the results of the experiment after 2 whole hours. As you can observe, 2 observations. First one would be that the brown deposits of copper are totally at the bottom of the test tube. That the zinc strip has sort of like disintegrated and made way for copper to totally just deposit on itself. So the brown deposit is copper. And secondly, you will notice that the blue color of copper sulfate has totally decolorized, indicative that the displacement reaction has successfully taken place, whereby zinc has displaced blue copper 2+ from copper 2 sulfate solution. So this was a simple demo to show the displacement reaction between zinc and copper 2+. So it can be observed that zinc has displaced blue copper 2+ from copper sulfate solution. Hence, by the end of 2 hours, the copper 2 sulfate solution is almost colorless because there is almost no copper 2+ inside. That all the copper 2+ has become copper metal, as you can see deposited at the bottom of the test tube. So, how is the chemistry of it illustrated? Because zinc is more electropositive than copper, therefore zinc will displace copper from copper 2 sulfate solution. The oxidation half equation would be that zinc has released 2 electrons to become zinc 2+, while the reduction half equation would be that copper 2+ has gained 2 electrons to become copper metal. Overall equation would be zinc reacts with copper 2+ to produce zinc 2+ as well as copper. And the substance oxidized will be zinc, while the substance reduced will be Cu2+. So in this case here, substance oxidized is very easily zinc. As you can see, zinc has released electrons, while the substance that has been reduced will be the copper 2+, which is blue in color because it has received electrons to become solid copper. So let's look at a second example of a displacement reaction whereby copper reacts with silver nitrate solution. So in the slide, you notice that there is a test tube of silver nitrate solution and copper is added. So the observation would be that the colorless solution actually turns to gray. Now why is that so? So let's look at the chemistry behind it. In the oxidation half equation, copper actually has been oxidized to copper 2+ and 2 electrons. So reduction half equation would be silver ion has accepted an electron to become silver metal. So the overall equation would be that copper reacts with 2 moles of silver ions to produce copper 2+ as well as 2 moles of silver atoms. So it can be observed that the substance oxidized will be copper, while the substance reduced will be silver ion. So in this case here, because copper is more electropositive than silver, so therefore copper is able to displace silver from silver nitrate solution. And the substance oxidized will be copper because it has released electrons, while the substance reduced will be silver ion because it has gained electrons. So the second observation that one should predict to see would be that silvery grey crystals are formed, indicative of the presence of silver metal form. Next up, let's look at displacement of halogen from its halide solution, whereby the strength of halogens as oxidizing agents decreases down the group. Generally, halogens are good electron acceptors and therefore are good oxidizing agents. So let's look at a simple setup whereby there's a reaction of chlorine with potassium iodide. So chlorine solution is added drop by drop into a test tube that contains colorless potassium iodide solution. So after the test tube is shaken, the observation would be that the colorless solution turns to brown, indicative of the presence of iodine. If the organic solvent tetrachloromethane is added into the test tube and shaken, the observation would be the tetrachloromethane layer becomes purple, further verifying the presence of iodine in the test tube. So we're trying to show you that even within halogens in the group 17 series, they can displace each other. Because what happens for that experiment will be, if you look at the half equation, in the oxidation reaction, iodide becomes iodine by releasing 2 electrons, while in the reduction half equation, chlorine has gained 2 electrons to become 2 chloride ions. So the overall equation would be that 2 moles of iodide ions has reacted with chlorine to produce iodine and 2 chloride ions. The substance oxidized will be iodide ion, substance reduced will be chlorine because chlorine has undergone oxidation while iodide ion has been reduced respectively. So if we refer back to the slide about the color of halogens in aqueous solution and CCl4, please refer to the slide that if the halogen is chlorine, the color of halogen in aqueous solution should be greenish yellow, while in an organic solvent like tetrachloromethane, it should be colorless. For bromine, the color of bromine in solution is brown, while if bromine is dissolved in CCl4, it would still be brown color. For iodine, it is brown in aqueous solution, but if dissolved in CCl4, it would be purple color. So that's why in the simple demo, as mentioned earlier, because chlorine being more reactive than iodide ions was able to displace iodide from potassium iodide solution, therefore producing iodine. Iodine in aqueous solution was brown, but upon addition of CCl4 turns purple. So let's move on to a detailed explanation about oxidizing agents. That oxidizing agents are substances which is reduced and its oxidation number decreases, and they are substances which gain electrons. Note, halogens are good oxidizing agents. The most reactive halogen, which is fluorine, is the strongest oxidizing agent. Metal ions, which are situated low in electrochemical series, are easier to be discharged. Such ions are example copper 2+, silver plus. They are good oxidizing agents. So this slide is just to tell you that halogens generally are good oxidizing agents, meaning that they have very strong ability to release, to give away their electrons, because oxidizing agents are reduced. So they are able to actually oxidize metals which are situated low in the electrochemical series. Now, let's look at question 1 for today's lesson. Complete the table below for the reactions of oxidizing agents. And the oxidizing agents are listed in the first column, and students are asked to write down the half equations which happen and the observations, if any. As we just finished the explanation on oxidizing agents, so let's look at the answers. So, if you can observe, fluorine, because it is the strongest oxidizing agent, will actually gain electrons to become fluoride ions. So the observation would be from pale yellow to colorless, because fluorine is pale yellow. So for chlorine, chlorine gains 2 electrons to become 2 chloride ions. Observation also pale yellow to colorless. Bromine will gain 2 electrons as well to become 2 bromide ions, and you will see a change from brown to colorless. For the manganate ion, manganate plus 8H plus 5 electrons will become Mn2 plus, giving you 4 moles of water. So the change in color will be from purple to colorless. For the dichromate ion, Cr2O7 would react with 14 moles of protons as well as 6 electrons to produce 2 moles of chromium ions, as well as giving 7 molecules of water. Change in color, orange to green. For copper 2+, it gains 2 electrons to become solid copper, and observation will be from blue to colorless. Or we could say that a brown solid is also formed, indicative of the presence of copper. For silver ion accepts an electron to become silver, so grayish white crystals are formed, indicating the presence of silver. So for hydrogen peroxide, it accepts 2 protons and 1 electron to become water. There should be no observation because hydrogen peroxide and water, they are both colorless. So the observations noticed will be the change in the reaction before and after. So that was all about oxidizing agents. Let's look at the definition of reducing agents. That they are substance which is oxidized, its oxidation number increases, and the substance which donates electrons are all definitions of reducing agents. So electropositive metals are good reducing agents. Metals which are very electropositive are very good reducing agents. Among the alkali metals, potassium is the strongest reducing agent. Among the halide ions, the iodide ions are the strongest reducing agents. So these actually are very good explanations on reducing agents that basically tells you that potassium is the best and the strongest reducing agent, while among the list of the halogens, iodide ion is the strongest reducing agent, therefore making the fluoride ion the weakest reducing agent because fluoride ion is the strongest oxidizing agent. So let's have a short recap for today's lesson. That we basically looked at a few simple setups on displacement reactions. That it's important to note that the more electropositive metal will always be able to displace the less electropositive metal from its salt solution. And then after that, we looked at the electrochemical series in greater detail and the definitions, followed by displacement of halogen as well from its halide solution. And we looked at detailed explanation of oxidizing as well as reducing agents. So that's the short recap for today. So that ends our lesson for today. Thank you so much for watching iTTV. We look forward to seeing you again the next time and have a great day.